Hello everyone, so in this video I'm going to discuss heat chapter except KTG and thermodynamics, which I have already covered in other videos. So again it's going to be a revision video, so I'm not going to discuss concepts in detail, but we have the idea about the concept and we'll see the application of that concept. So I have identified around 16 problem types considering the recent PYQs pattern. So first let us have a look at the syllabus for this chapter. So we have heat, temperature, thermal expansion, specific heat capacity, calorimetry, change of state, latent heat, heat transfer, conduction, convection and radiation. So as far as this convection is concerned, there won't be any numerical from this part. So I would suggest to go through what do you mean by convection, right? So go through that. That is more than sufficient for convection. Now let us start with the problem types. So the very first problem type is based on the linear temperature scale, right? So what is linear temperature scale? Let us see. If you look at the Kelvin scale, the freezing point, we can say the freezing point of for water will be 27.15, whereas the boiling point is 37.3.15. Similarly, for the Celsius scale, the freezing point is 0 degrees Celsius and the boiling point will be 100 degrees Celsius. And for the Fahrenheit scale, it will be 32 degree Fahrenheit for the freezing point, and for boiling point it will be 212. So these temperatures you should remember, right? These are the fixed temperatures. Now, if I want to convert from one scale to the another scale, and we are considering linear scales, what do we mean by linear scale? If I plot, say, on the y-axis as Fahrenheit, degree Fahrenheit, and on the x-axis we have degree Celsius, and let us say it's a straight line, okay, because it's a linear scale. So we can say if this point corresponds to, say, 0 degree Celsius, okay, and or this corresponds to 32 degree Fahrenheit, then this point is 100 and this will be 212, right? Now by using this logic, we can convert from one scale to the another. How we can do that? Just look at this important formula. Temperature on one scale minus lower fixed point upon upper fixed point minus lower fixed point is equals to temperature on other scale minus lower fixed point upon upper fixed point minus lower fixed point. Let us see the application of that. So if we consider Kelvin and Celsius, so K, let's say K is the temperature in Kelvin minus temperature, like freezing point of water will be 273. I'm taking just 273, right? For sake of easier calculation, divided by upper temperature minus lower fixed temperature. So that will be 373 minus 273, and that should be equals to, for Celsius scale, it will be, say, C minus 0 divided by upper minus lower, so 100 minus 0. Similarly, you can, if I want to again compare these two scales with the Fahrenheit, you can write this as F minus 32 divided by 212 minus 32. With this comparison, we can, with this relation, we can find, we can compare temperatures in two different scales. Now, let us the question based on this concept. So, on a Celsius scale, the temperature of the body increases by 40 degrees Celsius. The increase in the temperature on a Fahrenheit scale, right? So, we know that when the temperature changes from 0 to 100 degrees Celsius. In case of Fahrenheit scale, the temperature changes from 32 to 212 degree Fahrenheit, right? So we can say 100 degree Celsius change is equivalent to 180 degree Fahrenheit change. So by using this proportionality, or by using this relation, we can say 100 degree Celsius corresponds to 180 degree Fahrenheit. So 100 degrees Celsius corresponds to 180 degree Fahrenheit change. So 40 degrees Celsius will corresponds to 180 divided by 100 times 40. So here I am using the unitary method. So that will be 72 degree Fahrenheit. So option 3 is the right answer. Now let us see another question based on the same concept. On a temperature scale X, the boiling point of water is 65 degree X and the freezing point is minus 15 degree X. Assuming the scale, X scale is linear, the equivalent temperature corresponding to minus 95 degree X on a Fahrenheit scale. So again we're going to use the formula X minus freezing point of water will be minus 15 divided by upper 65 minus of minus 15, right? The equivalent temperature corresponding to minus 95. So we can say on a Fahrenheit scale. So F minus 32 is the freezing point of water in Fahrenheit scale divided by 212 minus 32. So let us solve this. X plus 15 divided by 80 is equals to F minus 32 divided by 180. So we can cancel this 0, this will be 4 and this will be 9. So we get 9x plus, and this will be 135 is equals to 4f minus, this will be 8 and 12. Okay, so we have to find the value for minus 95. Let us put x as minus 95. So that will be, I think it would be better if we put x minus 95 in this equation only. So we can say it will be minus 95 plus 15. I'm just putting the value in this equation, divided by 80 is equals to f minus 32 divided by 180. So this will be nothing but minus 1. So f will be 32 minus 180. So that will be minus 148. So option 4 is the right answer. So a faulty thermometer reads 5 degree Celsius in melting point and 95 degree Celsius in steam. The correct temperature on the absolute scale will be, we have to find in Kelvin when the faulty temperature reads 41. Okay, right. So again we're going to use the same formula. So let us say 41 minus 5 upon upper minus lower, that is for the faulty one, equals to K minus 273 divided by 373 minus 273. So this will become 36 and this will be 90, and then times 100 equals to K minus 273. So this will get cancelled out. This will give us 4. So K comes out to be 273 plus 40, and this will be 313. Okay, so 313 is the answer of this question. Now let us say the another illustration based on the same concept. So we have given the graph between two temperature scales P and Q is shown in the figure, but between the upper fixed points and the lower fixed points there are 150 divisions, equal divisions on the scale of P, and 100 equal divisions on the scale of Q. Uh, the relationship for the conversion between the two scale is given by, okay, right. So let me first write down the important coordinates. So we can say if this is 150 and it is 180, so this will be 30, right? And this point will be, we can say 100 comma 180, right? Okay, now we have to find the conversion, right? So in case of a scale P, the upper fixed point is 180 and the lower fixed point is 30. And in case of scale Q, the upper fixed point is 100 and the lower fixed point is 0. So let us write down here. So temperature in scale P minus lower fixed point, which is 30, divided by 180 minus 30. And that should be equals to temperature in scale Q minus 0 divided by upper fixed point, which is 100 minus 0. So this will be Tp minus 30 divided by 150, and that will be equals to Tq divided by 100. So if you look at the option 2 is the right answer. Right, so now we're going to see some concepts, and then there will be different problem types based on these concepts. So the first concept is the specific heat capacity, and what do we mean by that? It is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. So if the heat supplied is given to you, mass of the substance is given to you, and the change in temperature is given, so we can find the specific heat capacity, right? And in case of ice, the specific heat capacity is 0.5 calories per degree Celsius per gram, and in case of water it is 1 calorie per degree Celsius per gram, and in case of steam it will be 0.48 calories per degree Celsius per gram. And sometimes for numericals, we also take the specific heat capacity for steam nearly as 0.5 for the sake of easier calculation. Right, but if we have to compare the specific heat capacity for water and steam, then you have to water, not for water, for ice and steam, then you can take 0.48, right, for the specific heat capacity for steam. The second concept is the heat capacity. It is the amount of heat required to raise the temperature of entire body by 1 degree Celsius, whole body. And it is defined as delta Q by delta T, where delta Q is the heat supplied and delta T is the change in temperature of the body. And the third concept is the water equivalent. It is the amount of water which requires the same amount of heat for the same rise in temperature as that of the body. For example, this is the body. We have supplied delta Q amount of heat and the increase in temperature is delta T. So we can write this relation. Delta Q is equals to ms delta T, where S is the specific heat capacity of the body. Now if you apply the same amount of heat to water and the rise in temperature is also the same delta T, then we can say delta Q is mass of water times the specific heat capacity of water times delta T. Now if we compare these two equations, then we will get mass of ms equals to mw times sw. So mw is defined as the water equivalent of that particular body. Sometimes water equivalent is given, so then you can replace the body with water. Now the next concept is latent heat of fusion. So it is the heat supplied to a substance which changes its state from solid to liquid at its melting point, and the temperature is 1 atmosphere. This is known as the latent heat of fusion. And in case of ice, if you want to fuse ice to water, the heat required is 80 kilocalorie for per kg. So this value you have to remember, 80 kilocalorie per kilogram or 80 calories per grams. Now next is the latent heat of vaporization. Right, so it is the heat supplied to a substance which changes its state from liquid to vapor at boiling point at 1 atmosphere pressure. And for water, if water converts to steam, for conversion of 1 kg of water to steam, 540 kilocalorie of energy is required. So again, you have to remember this is the latent heat of vaporization for water. And the next concept is the heat curve, where we plot the temperature versus the heat supplied. Now here we're going to let me take a case of 1 gram of ice, which is at minus 20 degrees Celsius, right? Now, when we supply heat to the ice, what happens? The temperature of the ice will increase up to 0 degrees Celsius. So we can say delta Q will be ms delta T. So we can say delta T by delta Q will be 1 upon 0.5, right? So which is nothing but 2. So from this we will get the slope of this curve, right? Where on the y-axis we have temperature, on the x-axis we have heat supplied. So delta T by delta Q will be the slope. So tan theta 1 will be nothing but 2. But if you consider, like, once the ice reaches 0 degrees Celsius, what happens? Now whatever heat you supply, it will try to change the state of the ice from solid to liquid, right? So now the phase will change. When phase changes, the temperature doesn't change. So suppose we want to convert 1 gram of ice which is at 0 degrees Celsius to water at 0 degrees Celsius. We know the latent heat of fusion for ice is 80 kilocalorie per kilogram, and for 1 gram it will be 80 calories. So we have to supply 80 calorie of energy and we'll be able to change 1 gram of ice completely into water. So this horizontal line tells us that. Now beyond that, if you want to increase, let us see. Now we have water at 0 degrees Celsius. Now we want to convert water into, we want to increase the temperature of water to 100 degrees Celsius. So how much? So we can say delta Q will be 1. 1 is the mass, S is the specific heat capacity of water, and delta T is the change in temperature. So from this we can say the slope will be nothing but 1. So this is theta 2, right? So tan theta 1 was 2 now, and tan theta 2 is 1. So it means this theta 2 is less than theta 1, right? Okay. Now we have reached at this particular point where the water is having a temperature of 100 degrees Celsius. Now if you supply heat to water which is at 100 even more, then the temperature will not change, because now the phase of water will change, right? Now it will turn into from liquid to vapors. Now whatever heat you supply will try to change the state. Now in this region, when the entire water converts into steam, right, how much heat is required? So 540 calories of heat is required to convert water at 100 degrees Celsius to steam at 100 degrees Celsius. Now once we have steam at 100 degrees Celsius, now we can increase the temperature of steam. Now we have steam at 100. To increase the steam temperature beyond 100, delta Q required will be 1 S delta T. So we know that the specific heat capacity for steam is 0.48 calories per gram per degree Celsius. So here we have taken 0.48. So from this, delta T by delta Q will be 1 upon 0.48, which is greater than 2. So tan theta 3 is greater than tan theta 1. So we can say theta 3 will be greater than theta 1 and it will be greater than theta 2. So this relation you have to remember, this graph as well as the relation between the angles. Because usually they can ask you some qualitative questions where they will say like which slope is greater. Okay, let me also mention theta 1. So this will be theta 1. Right, so now let us the next concept, and it is nothing but the temperature versus the time curve. And here we going to increase the temperature with the constant power. So we have 1 gram of ice at minus 50 degrees Celsius, and the rate at which we are supplying the heat energy is 1 calorie per second, let us say. Now, first, if you want to convert ice, or if you want to increase the temperature of ice from minus 50 to 0 degrees Celsius, then we can say delta Q is equals to ms delta T, and if you divide both sides with the time duration, so we can say delta T by delta T will be given as 1 upon 0.5, because this power, if you because we have taken power as 1 calorie per second, right? So delta T upon delta small t will be 1 upon 0.5, so we got this angle theta 1, right? So on the y-axis we have temperature, on the x-axis we have time. So here again you have to remember the nature of the graph. So here when we have ice at 0 degrees Celsius, if you supply, if you give more energy, then its phase will change. Now here we have water which is at 0 degrees Celsius. Now we are supplying heat at a constant rate, so the temperature of water increases. At this particular point we have temperature at 100 degrees Celsius. Now if we supply heat, the phase will change. So here water is being converted into steam, and at this particular point we have the entire water is converted into steam, and if you further supply heat energy, then the temperature of the steam will increase. So this graph you should remember, even the relation among the angles which I have mentioned. Right, so the next concept is principle of calorimetry. So here if we have suppose there is a copper vessel and it has two liquids, liquid 2 and liquid 1, and liquid 1 is having mass m1, specific heat capacity s1, temperature t1. Liquid 2 is having mass m2, specific heat capacity s2, temperature t2. And this copper vessel, which is nothing but the calorimeter, it is having mass m3, specific heat capacity s3, and temperature t3. Now according to the energy conservation, whatever heat exchanges are happening, their sum should be 0, right? So delta q net should be 0. So we can say the M1, S1 and T is the equilibrium temperature, final temperature. So M1, S1 times T minus T1, that is T1 is the initial temperature of the liquid one. Then M2, S2, T minus T2 and M3, S3, T minus 3T, this should be equals to 0. And by this relation, by this equation, we can find the equilibrium temperature of the system. Right, so now let us see the illustration based on the concept we have just discussed. Now let us see this question. A block of ice at minus 10 degrees Celsius is slowly heated and converted to steam at 100 degrees Celsius. Which of the following curve represents the phenomena qualitatively? So we have minus 10 degrees. So what will happen in this question? First, the ice which is at minus 10 degrees Celsius, its temperature will increase. So we have ice at 0 degrees Celsius, and it will be a linear graph, right? So first the graph should be linear, and then we have then the phase will change. Ice at 0 degrees Celsius will convert into water at 0 degrees Celsius. Now it will be a horizontal horizontal curve. Now we have water. Now the temperature of the water will increase. So water at 0 degrees Celsius, then we have water at 100 degrees Celsius. Now it will be a linear graph. Then there will be phase change. So water at 100 to steam at 100 degrees Celsius. So it will be horizontal line. So we can say it will be slant, horizontal, slant, horizontal. So let us see the option. Option 1 is incorrect. Option 2 is incorrect because it is saying first we have horizontal. Option 3 is incorrect. So option 4 is correct. Got it? So option 4 is the right answer of this question. Now let us see this question. Two different metal bodies A and B of equal mass are heated at the uniform rate under the similar condition. The variation of temperature of the bodies is graphically represents as shown in the figure. The ratio of the specific heat capacity is right. So if you look at the body A, this is the graph, okay, and we can very easily find the slope. Let us say this angle is theta A. Now tan theta A will be what? Perpendicular upon base. Perpendicular is 12 and the base 120, sorry, it is 120 and the base, this length is 3, so it comes out to be 40. Similarly, if this angle is theta B and in this right angle triangle we can say tan theta B will be 90 upon 6, so it will be 15, right? And we know that when we supply heat energy, let us say we are supplying delta Q and it will be ms delta T, right? And we are supplying heat at a constant rate, uniform rate. So we can say delta Q by delta small t is equals to ms delta T upon delta small t. Now this is constant. Let me call this as P. Mass is also constant for both the bodies. S and delta T by delta small t is nothing but the slope. So we can say this is constant. M is constant. Specific heat is different for both the bodies. So we can write this as specific heat times the slope, which is tan theta, should be constant. So we can say SA tan theta A should be equals to SB tan theta B, with SA is the specific heat capacity for the body A and SB is the specific heat capacity for the body B. So we can say SA upon SB is equals to tan theta B upon tan theta A. Tan theta B is 15, theta A is tan theta is 40, so this will be 3 by 8. So option 2 is the right answer. Right, so let us see the next question. 100 grams of iron nail is hit by a 1.5 kilograms hammer, striking at a velocity of 60 meters per second. What will be the rise in the temperature of the nail if 1/4 of the energy of the hammer goes into heating the nail? So we can say the energy in the hammer is nothing but the kinetic energy. So let us first see the kinetic energy. That will be half mass of the hammer, that will be 1.5 times the square of the velocity. So it say, and the question states that 1/4 of this is converted in heating the nail. So if we divide this by 4, this will be nothing but the heat which is being used to increase the temperature of the nail. So we can write this as ms delta, the mass of the so this will be 100 grams. If you multiply this with specific heat capacity, which is in joules per gram per degree Celsius, so that will be 0.42. So this and the increase in temperature, let us say it is delta T, right? So we can write this as 1.5 times 3600 divided by 8. So this will give us 450 and that will be 42 delta T 450. So if we simplify this, so 450 times 1.5 divided by 42, so this comes out to be 16.07 degrees Celsius. So that is the increase in temperature. So option C is the right answer. Right, so now let us see the next question. A geyser heats water flowing at a rate of 2 kilogram per minute from 30 degrees Celsius to 70 degrees Celsius. If the geyser operates on a gas burner, the rate of combustion of the fuel will be, so we have to find the rate of combustion which is in grams per minute. And the heat of combustion is also given. If we burn 1 gram of the fuel, we'll get 8 into 10 raised by 3 joules of energy. And specific heat capacity of water is also given, which is 4.2 joules per gram per degree Celsius. Right, so we want to at what rate we have to heat the water? 2 kilogram per minute. So in 1 minute, let us study for 1 minute. We want to heat 2 kilograms of water from 30 to 70. So how much heat is required? That will be 2 ms, and specific heat capacity is, okay, let me convert this into grams. So 2000 grams multiplied with 4.2. Why I have converted this into grams? Because specific heat capacity is joules per gram per degree Celsius. It is in grams now. So times 4.2 times the increase in temperature 40. Right, so that is the amount of heat energy required for 1 minute. And we have given that to get 8 into 10 raised by 3 joules, 1 gram is required. So let us see how much gram will produce that much amount of heat energy. So we can say, let us say m is the amount of grams which produce that much amount of energy. So it will be delta Q divided by heat of combustion, which is 8 into 10 raised by 3, and this will give us answer in grams, right? So so let us simplify this. So 2000 times 4.2 times 40 divided by 8 into 10 raised by 3. So this will get cancelled out. This will give us 5. So it will be 42 grams. So we require 42 grams per minute. So the answer should be 42. Right. So the next concept is calorimetry. Uh, a copper block of mass 5 kilogram is heated to the temperature of 500 degrees Celsius and is placed on a large ice block. Right. So we have given a large ice block and we have placed a copper block which is having a mass of 5 kilograms and its current temperature is 500 degrees Celsius. Now, what is the maximum amount of ice that can be melted? So we can assume when this copper block attains 0 degrees Celsius, the energy lost by this copper will completely be utilized in melting the ice. So we can say energy or heat lost by copper block will be equals to heat gain to melt ice. So what is the heat loss? The temperature of the ice block is going down from 500 to 0 degrees Celsius. So we can say it will be ms. Specific heat capacity for copper block is 0.39 joules per gram. Again, it is given in per gram. So let us first convert 5 kg into grams. So multiply this with 1000 times 0.39 is the specific heat capacity times the change in temperature, which is 500. And heat gained to melt the ice. So we have given latent heat of fusion. So it is 335 joules per gram. So let us say m amount of ice has melted. So m times the latent heat of fusion, which is 335. Okay, now let us simplify this. So we have 5000 times 0.39 times 500 divided by 335. So this will give us m as 2910 gram. Yes, this will be in grams, right? Because this 335 is in joules per gram. So we got m as 2.2910 grams and we have to find the answer in kilograms. So option C is the right answer. Now let's see the next question, and it's based on phase change. A block of ice of mass 120 grams at temperature 0 degrees Celsius So we have ice, which is having a mass 120 grams, temperature 0, is put on a 300 grams, put in a 300 grams of water at 25 degrees Celsius. The x gram of ice melts as the temperature of the water reaches 0 degrees Celsius. So what is happening in this case? The water, um, the uh, the water is supplying heat energy to ice, right? So we can say heat lost by water is equals to heat gained by ice. So what is the heat loss? Water's temperature is 25, so it is coming down to 0 degrees Celsius. Mass is how much? 300. And specific heat capacity of water is given in terms of joules per kilogram per Kelvin. So we can take water in kilograms. So we can say 0.3 times 4200 times the change in temperature, which is 25, and that should be equals to heat gained by the ice. So let us say x grams. So they have given x grams of ice is melting. So we can say it will be x grams. So okay, let us find the mass in kilograms, right? Let us say this is m, which is in kilograms. Multiply this with 3.5 into 10 raised per 5 joules per kilogram. So this will give us answer in kilogram. Then we have to convert that into grams. So let us simplify this. So we have 0.3 times 4200 times 25 divided by 3.5. So it will be 9000 divided by 10 raised per 5. It will be in kilograms. So we can write this as 9 into 10 raised per 6 upon 10 raised per 5 grams. So this will give us 90 grams. So x will be 90. So 90 is the answer of this question. Right. So now let us see the next question based on the same concept, phase change. A lead bullet penetrates into a solid object and melts. So this lead bullet melts, assuming that 40% of its kinetic energy is used to heat it. The initial speed of the bullet is, so we have given initial temperature of the bullet is 127 degrees Celsius. Melting point of the bullet is 327 degrees Celsius. Latent heat of fusion of the lead is 2.5 into 10 raised per 4 joules per kilogram, and the specific heat capacity of lead is 125 joules per kilogram per Kelvin. So here what is happening? A bullet which lead bullet, let us say this is the lead bullet which is traveling with certain kinetic energy. It is having a velocity, let us say v, or kinetic energy will be half mv square. So 40% of this is being utilized to heat up this lead bullet. So 40% means 0.4 into half mv square is being utilized to heat up the bullet. So first the temperature of the bullet will rise, and then the phase will change. So the heat required to change the temperature of the bullet from 127 to 327 will be m. Specific heat capacity is 125 times, so I'm taking m in kilograms, times the increase in temperature from 127 to 327 will be it will be 200, plus the phase change, the heat supplied required for the to fuse the lead bullet. So it will be mass times the latent heat of fusion, and that is 2.5 into 10 raised per 4. So that will be 2.5 times 10 raised per 4. Right, so let us simplify this. So m will get eliminated everywhere, so on the left hand side and the right hand side, and it will be v square, and it will be 0.2. So v square by 5 equals to 250 times 100 plus, okay, let me write it here. V square by 5 is equals to 250 times 100 plus 250 times 100. So this comes out to be 2 times 250 times 100 times 5. This will be V square. So it got 500 times 500, that is V square. So V comes out to be 500 meters per second. So option B is the right answer. Right, let us say the next question based on the same concept. Heat energy of 184 kilojoules is given to ice of mass 600 grams at minus 12 degrees Celsius. Specific heat of ice is 2222.3 joules per kilogram per degree Celsius. So specific heat is given. Latent heat is also given for ice, that is 336 kilojoules per kilogram. Now we have to check which options are correct. So A is given as final temperature of the system will be 0 degrees Celsius and final temperature of the system will be greater than 0 degrees Celsius. The final system will have a mixture of ice and water in 5:1, and the final system will be having a mixture of ice and water in the ratio 1:5, and E is the final system will have water only. Right, so let us see what is happening in this case. So first of all, we have given ice which is having a mass of 600 grams and its temperature is minus 12 degrees Celsius, and we are supplying 184 kilojoules of heat energy. So first let us see whether this energy is sufficient to change the temperature of ice from minus 20 to 0. Let us see. So delta Q required from minus 12 degrees Celsius to 0 degrees Celsius. So it will be M. Specific heat capacity is given in kilograms, no, joules per kilogram. So it will be 0.6 times 2222.3 times the change in temperature will be 12. Okay, so that will be 0.6 times 2222.3 times 12. So this comes out to be 16 into 10 raised to power 3, and it will be in joules. So we can say it is nothing but 16 kilojoules. So 16 kilojoules of energy is required, right? So now the ice is at that much temperature. Now let us find the energy required to melt that much amount of ice. So let us find that energy. So delta Q from required to for ice at 0 to water at 0 degrees Celsius. So this will be mass, which is 0.6 times the latent heat of fusion. It will be 336 kilojoules. So if we multiply 336 with 0.6, we are getting 201.6 kilojoules. But if you look at the energy required, it is 184. So it means the entire ice will not able to melt. So let us see how much amount of ice will melt. So let us say M amount of ice will melt. So M times 336 kilojoule, and that will be equals to how much? So we have 184 kilojoules minus 16 kilojoules, right? So that will give us the amount of ice which will melt. So it will be 168 divided by 336, right? So 168 divided by 336, so this comes out to be 0.5 kilograms, right? 0.5 kilograms. So it means in the final mixture, we'll be having 100 grams of ice and 500 and rest is 500 grams of water, because 500 grams of ice has melted into water. So if you take the ratio of ice to water, it will be 1:5. So it means option C is correct, and the final temperature will remain 0 degrees Celsius because the entire ice has not melted into water. So A is also correct, right? So A and C, so option 4 is the right answer, right? So now let us see the next question based on the same concept, phase change. 1 gram of liquid is converted to vapor at 3 into 10 raised to 5 Pascal pressure. If 10% of the heat supplied is used for increasing the volume by 1600 cubic centimeter during this phase change, then the increase in the internal energy in the process, right? So here we can apply first law of thermodynamics, which says that delta Q is equals to delta U plus delta W. And in the question, they have clearly mentioned that 10% of the heat supplied is used for increasing the volume, right? So we can say delta W will be nothing but P times delta V, and pressure is 3 into 10 raised to power 5. Pressure is constant, and change in volume is 1600 cubic centimeter, which is 1600 into 10 raised to power minus 6 cubic meter. So this comes out to be 48 into 10 raised to power 7 minus 6, so it will be 480 joules. So that we got the value of delta W, and we have to find the increase in energy, and 10% of the heat is used. So we can say 10% of delta Q is nothing but delta W, and delta W is 480. So delta Q is 480 divided by 10%, which is 0.1, so it will be 4800 joules. Now we got delta Q, we know what is delta W, so delta U will be 4800 minus 480, so which comes out to be 4320 joules. So option 1 is the right answer. Right, so now let us see the next concept, which is based on thermal expansion. Let us first have some idea about this concept. So in case of a linear expansion, we can say the fractional change in the length will be alpha times delta T, where alpha is the thermal coefficient of linear expansion. And in case of a aerial body or sheet-like body, the fractional change in the area will be 2 alpha times delta T, where alpha is the coefficient of linear expansion and 2 alpha is the coefficient of aerial expansion, thermal coefficient of aerial expansion. And we can write, usually this 2 alpha can also be written as beta, and similarly in case of volume, this 3 alpha can be written as gamma. And we can write beta as 2 alpha and gamma as 3 alpha only in case of isotropic body which are expanding equally in all direction. So this you have to remember. Now let's say the question based on the linear expansion. At what temperature a gold ring of diameter 6.230 centimeter is be heated so that it can be fitted on a wooden bangle of diameter 6.241 centimeter? Both the diameters have been measured at the room temperature 27 degrees Celsius. Given that the coefficient of thermal expansion of gold is 1.4 into 10 raised to power minus 5 per Kelvin. Right, so here we have given a gold ring which is having a diameter 6.230 centimeter and its temperature is 27 degrees Celsius. Now we're going to increase the temperature, then the diameter will increase. And what happens in case of a in case of a thermal expansion? The new shape will be the photographic enlargement of the body, right? So every dimension will increase. So we can say the if this is d, then this diameter will be d plus delta d. So we can say delta d by d is nothing but alpha times the increase in temperature, right? So we can apply this for the diameter. And what is the increase in the diameter? So we have to increase the diameter of the ring from 6.230 to 6.240. So the increase in diameter will be 6.241 minus 6.230, which will be 0.011 centimeter. So 0.011 divided by d, so I'm going to substitute the values in this equation, upon 6.230 will be equals to alpha, which is 1.4 into 10 raised to power minus 5 times the increase in temperature. And we have to find the final temperature, right? So let's first find the change and then we can simply find the final temperature. So it will be 11 divided by 6230 divided by 1.4 multiplied with 10 raised to power 5, and it comes out to be 126.1 degrees Celsius. So delta theta is nothing but final temperature minus initial, which is 27. 126.1 degrees Celsius. So the approximate answer will be 126 plus 27. So it will be 153. So option D is the right answer. Now let us see another question based on linear expansion. A unit scale is to be prepared whose length does not change with temperature. Okay, so the length is not changing with temperature and it remains as 20 centimeter. Using a bimetallic strip made of brass and iron, each of different length, the length of both the components would change in such a way that the difference between their lengths remain constant. If the length of brass is 40 and the length of iron will be, okay, right. So let us say LB is the original length of brass and length for iron is given as, that we have to find, and this is given as 40. And we have clearly mentioned in the question the length of both the component would change in the same way, in such a way that the difference between their length remains constant. So it means the change in the length of brass is same as the change in the length of iron. So we can say delta L, and we know this formula delta L by L will be alpha times delta theta. So we can say delta L can be written as L alpha delta theta. So for brass it will be for brass delta L will be L B alpha B times delta theta, and for iron it will be Li alpha I times delta theta. And their length, the difference of their length doesn't change, so it means the increase will be same in both the material. So it means Lb alpha b delta theta will be equals to Li alpha I delta theta. So this will give us Lb alpha b equals to Li alpha I. So alpha for brass is given, iron is given, and we have to find the length for iron. Okay, length of iron. So Li will be 40 times 1.8 into 10 raised per minus 5 divided by 1.2 into 10 raised per minus 5. So this will cancel. It will be 3, 2, 20. So this comes out to be 60 centimeter, right? So 60 is the answer of this question, right? So let us see this question based on linear expansion. A hole is drilled in a metal sheet at 27 degrees Celsius. The diameter of the hole is 5 centimeter. When the sheet is heated to 177 degrees Celsius, the change in the diameter of the hole is d into 10 raised to minus 3 centimeter. The value of d will be if the coefficient of linear expansion of metal is 1.6 into 10 raised to minus 5. Right, for the diameter we can say it will be delta d upon small d equals to alpha times delta theta. And the change in the diameter is given as d into 10 raised to minus 3 centimeters. And the original diameter is 5 centimeter, equals to alpha 1.6 into 10 raised to minus 5, and the increase in temperature, so temperature is increasing from 27 to 177, so which is nothing but 150, right? So from this it comes out to be 16 5 is 8 6 1, 5 times 1.6 is 8, so 8 times 150 times 10 raised per minus 5 divided by 10 raised per minus 3, so that will be d. Okay, right, so this will be 1200 into 10 raised per minus 2, which is 12. So 12 is the answer of this question. Now let us see the question based on volume expansion. A solid metallic cube having the total surface area 24 square meter, right? So they have given total surface area for a metallic cube. So we know that total surface area is 6 times the area of one of the face, which is a square, where a is the length of one h. This is given as 24, so a square will be 4, a will be 2 meters. Now we got the side of the cube. If its temperature is increased by 10 degrees Celsius, calculate the increase in the volume, right? So we know that delta V is equals to V gamma delta theta, where gamma is the thermal coefficient of volume expansion, and here we have given alpha, so we can write gamma as 3 alpha. So V original volume will be a cube, so 2 cube, and gamma will be 3 times alpha, which is 5 into 10 raised to power minus 4, and the increase in temperature is 10. So this will be 8 times 15 times 10 raised to power minus 3. So this comes out to be 120 into 10 raised to power minus 3, and it will be in meter cube, and we have to find the answer in centimeter cube. So this will be 120 into 10 raised to power minus 3, 10 raised to power 6 centimeter cube, and it will be 120 into 10 raised to power 3, or 1.2 into 10 raised to power 5 centimeter cube. So option 2 is the right answer. Now let us see another question based on the same concept. Each side of the box made of metal sheet in cubic shape is A. So side is A and the room temperature is T. The coefficient of linear expansion of the metal sheet is alpha. The metal sheet is heated uniformly by a small temperature delta T, so that its new temperature becomes T plus delta T. Calculate the increase in the volume of the metal box. So direct application of the formula. So delta V by V is equals to gamma, which is 3 alpha times delta T, where delta T is the increase in temperature. So delta V can be written as, and it's a cube, so it will be 3 times A cube alpha delta T. So option 1 is the right answer. Now let us see the next question. Energy stored in the linear expansion. The area of cross section of a railway track is 0.01 square meter, and the temperature variation is 10 degrees Celsius. Or you can say temperature is increasing by 10 degrees Celsius. The coefficient of linear expansion of the material of the track is 10 raised to power minus 5 per degree Celsius. The energy stored per meter in the track length in the track is per joule, is in that we have to find the answer in joules per meter. So Young's modulus is also given for the track, that is 10 raised to power 11. Let us say the length of the track is L. Right? So length is L, and temperature variation is given, delta theta is given 10 degrees Celsius. Area of cross section is given 0.01 square meter, and alpha is given, which is 10 raised to power minus 5 per degree Celsius. So here we have the variation, right? So variation is 10 degrees Celsius. So what we can say, if we treat this track just like a spring, right, which is having, sometimes it is elongating and then compressing. So in that case, in case of a rod, the equivalent spring constant is given as YA by L, right? Where Y is the Young's modulus, A is the area of cross section, L is the length, right? So the energy stored will be half K equivalent times delta L square. Delta L is the change in the length, and we have to find the energy stored per unit length, so divided by L. So this value we have to calculate. Let us put the value. So 1 by 2L times YA by L, and then delta L can be written as L alpha delta theta, right? So let us simplify this. So YA divided by 2L square times L square alpha square delta theta square. So this L square will get cancelled out. So we can say it will be 10 raised to power 11 times 10 raised to power minus 2, which is area, times alpha square, which is 10 raised to power minus 10, delta theta square, which is 10 raised to power 2, divided by 2. Okay, let us simplify this. So it will be 10 raised to power 13 times 10 raised to power minus 12. So it will be 10 by 2. So it comes out to be 5 joules per meter. So 5 is the answer of this question. Right, so now let us see the next concept, which is based on bimetallic strip. Let us see what are bimetallic strip. So here, if you look at this diagram, so here we have given two strips. Let us say the above one, the blue one is steel, and this one is copper, right? Now when we and the thermal coefficient for steel is less than the thermal coefficient of copper. So, but we can say for the same increase in temperature, the elongation in copper will be more than the elongation in steel. So, when you heat this bimetallic strip which are bonded together, then the length of the copper will be more than the length of the steel. So that's why it will curve in the upward direction, so that the length of copper is more than the length of steel. And on the copper side will be having a convex, on the steel side will be having a concave surface. So this concept you have to remember. Okay, let us see a question based on this concept. A bimetallic strip consists of a metal A and B. It is mounted rigidly as shown. The metal A has higher coefficient of expansion compared to that of metal B. When the bimetallic strip is placed in a cold bath, it will. Now, when we are decreasing the temperature, so the decrease in length for the metal which is having a higher coefficient of thermal expansion will be more, right? So decrease in length in that metal will be more. So metal A is having a higher coefficient, so the decrease in the length of A will be more. So it means now the shape will be like this. This is A and this is B. Okay, so the final length of B will be more than the final length of A. So option 4 is the right answer. Bend towards the left. Now the next concept is based on thermal stress and thermal strain. Now let us see what do we mean by that. Suppose there is a rod which is lying on a smooth surface, and now we are going to increase the temperature. So when we increase the temperature, there is no obstruction for the free expansion. So since there is free expansion, there will be no thermal stresses developed, there will be no thermal strain, right? So both will be zero. But suppose if we fix both the ends of the rod with a rigid support, right? Fixed ends. Now even if you increase the temperature, the length will not change. So we are increasing temperature from theta 1 to theta 2. So delta theta is the increase in temperature. So in this case, there will be some compressive, you can say tensile stresses developed, and there will be strain. Now what is that strain? So this strain will be nearly equals to alpha delta theta, where delta theta is the change in the temperature and alpha is the thermal coefficient of linear expansion for the rod. So this formula you have to remember. Now let us see the question based on this concept. Given below are two statements. One is labeled as assertion and the other is labeled as reason. When a rod lying freely is heated, no thermal stress is developed in it. That is fine. Option assertion is correct. On heating the length of the rod, increases. That reason is also like this statement is fine, but it is not the justification for assertion A. So it means both A and R are true, but R is not the correct explanation for A, so option 1 is the right answer. Now let us see this question. A steel rod of length 1 meter and cross-sectional area 10 raised to power minus 4 is heated from 0 to 200 degrees Celsius without being allowed to extend or bend. Okay, so it is a constrained expansion, you can say. The compressive tension produced in the rod is, so we have given Young's modulus for the steel rod, and we have given thermal coefficient of linear expansion also. So we know that the strain delta L by L will be given as alpha times delta theta. And if we apply Young's modulus formula, so we can say F by A is equals to Young's modulus times delta L by L. Now from this F will be YA delta L by L. So if you substitute delta L by L value in this formula, we'll get YA alpha delta theta. And this basically is the compressive tension developed in the rod, and it will be 2 into 10 raised per 11 times area of cross section, that is 10 raised per minus 4, alpha is 10 raised per minus 5, and the increase in temperature is from 0 to 200 to 200 degrees Celsius. So this will give us 4 into 10 raised per 11 minus 4 minus 5 plus 2. So it will be 13 10 raised per 13 minus 9, 4 into 10 raised per 13 minus 9, so it will be 4 into 10 raised per 4, and this answer is in Newton, and it will be so the answer in this for this question will be 4. So the next concept is based on conduction. So let us see what do we mean by that. So if we have given, say, a conductor which is having a circular cross section, and let us say A is the area of cross section, L is the length of the conductor, and the left cross section is maintained at a temperature T2, and the right end is maintained at a temperature T1, and let us say T2 is greater than T1. So in steady state we can say the rate of flow of energy, so or the rate of flow of heat, so delta Q by delta T will be given as Ka T2 minus T1 divided by L, where delta Q by delta T is known as the thermal current. So that is thermal current, and Ka by L, this is the reciprocal of thermal resistance. So 1 upon thermal resistance, and this T2 by T1 is nothing but the temperature difference. Now we can apply, like there is an analogy in this formula and the Ohm's law. Let us see the Ohm's law. In Ohm's law we have I equals to V2 minus V1 by R, where V2 minus V1 is the potential difference and R is the resistance. So here instead of like electrical resistance we have a thermal resistance. Instead of electrical current we have a thermal current. So we can apply all concepts that we have studied in current electricity in these types of question. So let us see some of the illustration. So here this problem type is based on the temperature of the junction. Now we have given two conductors which are joined together, and we have to find the temperature of the junction. So two plates A and B having the thermal conductivity is 84 watt per meter per Kelvin and 126 watt per meter per Kelvin respectively, and they have same surface area. So surface area is same thickness, means the length is same. They are placed in contact along their surface, and if the temperature of the outer surface of A and B are kept at 100 degrees Celsius and 0 degrees Celsius, then the temperature of the surface of contact in the steady state. So again we have to find in this question we have to find the temperature of the um, their interface, basically where they are joined together. So we have two plates. This is plate A and this one is plate B. Their thicknesses are same, so I'm taking this as L, this is also L, and their area of cross sections are same. Let us, this is small a and this is also small a. And the left end is maintained, outer surface of A which is not in contact with B is maintained at 100 degrees Celsius, and this end is maintained at 0 degrees Celsius. Okay, so what we can say, since these two conductors are in series, so if we have a thermal current, say I1 in this direction and I2 in this direction, then for series resistors we can say I1 will be equals to I2. And what is I1? That will be, let us say the temperature of the junction is T, so it will be 100 minus T, that is the temperature difference, divided by the thermal resistance, and thermal resistance will be L by Ka, right? L divided by thermal conductivity, which is 84 times the area of cross section. That should be equals to T minus 0 divided by L by 126 A. Now let us simplify this. So 100 minus T times 84A by L is equals to T times 126A by L. So this A by L will get cancelled out, and from this we will get this will be 42 and this will be 63. Okay, right, so this and this will be 14 and 21, or 2 and 3. So we can say 200 is equals to 5T, so T comes out to be 40 degrees Celsius. Right, so now let us see another question based on the same question, same concept. So if K1 and K2 are the thermal conductivities and L1 and L2 are the lengths, and A1 and A2 are the cross-sectional areas of steel and copper rods, such that K2 by K1 is 9, A1 by A2 is 2, L1 by L2 is 2. Then for the arrangement as shown in the figure, the value of the temperature T of the steel copper junction. So here we have to find the temperature. It is similar to the last question. So here we can say the thermal current in the steel should be same as the thermal current in the copper. So it will be 450 minus T divided by the resistance of the steel wire, which will be L upon Ka, and L in this case will be L2 upon steel. Okay, right. So it will be K1 basically. K L1 and K1, and this will be A1, and that should be equals to T minus 0 divided by L2 times K2 times A2. Right. So from this, what we can do, we have given the ratios. So we can say 450 minus T by T is equals to L1 by L2 times A2 by A1 times K2 by K1. So 450 minus T by T, L1 by L2 is 2, A2 by A1 is 1 by 2, K2 by K1 is 9. So 450 minus T is equals to 90, and T will be 45. So option C is the right answer. Now let's see one more illustration based on the temperature of junction question. So here we have given temperature theta at the junction of two insulating sheets having the thermal resistance R1 and R2, as well as the top and the bottom temperature are given, theta 1 and theta 2, and we have to find the temperature of the junction. So again, if we assume theta 2 is greater than theta 1, we can say the thermal current is flowing in the downward direction. So if this is I1 and this is I2, then I1 should be equals to I2, and I1 can be written as theta 2 minus theta divided by R2, and that should be equals to theta minus theta 1 divided by R1, right? So if we rearrange the terms, we will get option 3 as the answer, right? Now the next problem type is based on the equivalent thermal conductivity. Now here we have given two conductors in series. As per the given figure, two plates A and B of thermal conductivity K and 2K are joined together to form a compound plate. The thickness of the plates are 4 centimeters and 2.5 centimeters respectively, and the area of cross section is 120 square centimeter for each plate. The equivalent thermal conductivity of the compound plate is 1 plus 5 by alpha times K. Then the value of alpha will be. Now in this case, what we want to do, for the same dimension, let us say the area of cross section is A. Okay, that is given as 120 only, right? So let me call this as A. So if I replace these two conductors with a single conductor which is having an area of cross section A, and the length of this conductor will be nothing but the sum of the lengths of both the conductors. So that will be 6.5 centimeter, and let us say its thermal conductivity is K prime, and it will give us the same thermal current through this new material, let us say. Then we can say the two situations are identical to each other, and we are maintaining the same currents or same temperature at the ends. So what we can say, the thermal resistance of this new conductor should be same as the thermal resistance of this series connection. So we can say R1 plus R2 should be equals to R equivalent in series connection. R1 will be L1, which will be 4 centimeter, L by K, area of cross section, that will be, let me take it as A only, plus R2 will be 2.5 centimeter divided by 2K times area of cross section. It should be equals to 6.5 centimeter divided by the thermal conductivity of this equivalent thermal conductivity times the area of cross section, that is A. Now this A will get cancelled out, and this is centimeters, and it will become 8 plus 2.5 divided by 2K, and this will be equals to 6.5 by K prime. So this so K prime upon 6.5 will be 2k divided by 10.5. So this will be 13 and it will be 21. So k prime comes out to be 26 by 21 times k, and this can be written as 1 plus 5 by 21 times k. Now if you compare this result with this the given data, alpha is nothing but 21. So 21 is the answer of this question. Now let us see one more question based on the same concept. Two identical metal wires of thermal conductivity K1 and K2 are connected in series. The effective thermal conductivity of the combination is, so we have identical wire, right? So their dimensions are same. So this is the first wire, this is the second wire. Let us say the length is, this length is L, this length is also L, area of cross section is A, right? We want to replace uh, with this combination with a single wire which is having a thermal conductivity, let us say K prime. So this is K1 and this is K2. So we can say the thermal resistance of this equivalent will be same as the thermal resistance of this combination, right? So we can say L upon K1A plus L upon K2A should be equals to, this length is nothing but 2L, right? 2L upon K prime times A. So A will get cancelled out, L will get cancelled out. So 2 by K prime will be equals to 1 by K1 plus 1 by K2. So from this, K prime comes out to be 2 times K1 K2 divided by K1 plus K2. So option 1 is the right answer. Now let us see the another concept which is based on the phase change and the conduction process. So here we have both the formulas we have to use, the phase change concepts as well as this delta Q by delta T formula, which is Ka T2 minus T1 divided by L. Okay, an ice cube of dimension 60 centimeter, 50 centimeter and 20 centimeter is placed in an insulation box of wall thickness 1 centimeter. The box kept the ice cube at 0 degrees Celsius of temperature is brought to room temperature. So the box keeping the ice cube at 0 degree, now we are bringing that box in the room which is having a room temperature 40 degrees Celsius. The rate of melting of ice is approximately, so we have to find in terms of kilograms per second how much ice is being melted per second. Okay, right. So here we have given a container and the thickness of the container is also given. Thickness is 1 centimeter. So it means if this is if here we have ice which is at 0 degrees Celsius and surrounding outside we have 40 degrees Celsius. So it means the heat is entering the container from outside to inside, right? So here what is the total surface area? We can say the total surface area is nothing but 6 times we have given the dimensions, right? So it will be 2 times L into B plus B into H plus H into L. So it will be 2 times 60 times 50 plus 50 times 20 plus 20 times 60, and that will be in square centimeter. So let us simplify this. So that will be 200 and this will be 30 plus 10 plus 12. So it comes out to be 52. So 52 times 200. So it will be 10400 centimeter square. So that is the total surface area from where the heat is entering this cubical box. And latent heat of fusion is also given. So what we can say, delta Q by delta T will be thermal conductivity, which is 0.05. Area is, okay, let us first convert this area into meter square. So that will be 1.04 square meter. So 1.04 times the temperature difference, which will be 40, divided by the thickness, which is 1 centimeter 10 raised to -2. So this will be 5 into 1.04 times 40. which will be 2 into 104, that will be 208. So this comes out in joules per second, right? So that much amount of energy is getting is entered in this container in 1 second, and we have given the latent heat of fusion for ice, which is given as 3.4 into 10 raised per 5. So we can say dq by dt can also be written as d by dt of m times L, where L is the latent heat of fusion. So from this, 208 can be written as L times dm by dt, and dm by dt is nothing but the rate at which the ice is getting melted. So 208 divided by 3.4 into 10 raised per minus 5, that will be the rate of melting. So let us simplify this. So 208 divided by 3.4, so it will give us 61.1 into 10 raised per 5. This is plus 5, sorry, not minus 5, this is plus 5. So option B is the right answer. The next concept that we're going to discuss is black body radiation, and here we'll talk about Wien's displacement law. So here on this graph, on the y-axis, we have given intensity per unit wavelength interval, or you can say this will be di by d lambda, and on the x-axis we have given lambda. And if you take the area under the graph, so it is nothing but, let me write here, so integral d lambda di by d lambda times d lambda, so d lambda will get cancelled out, and this will give us the total intensity which is being radiated by the body at a particular temperature. So if the area is more, then we can say the intensity will be more. So higher the temperature, the area under the graph will be more. Second point is, for a long and the short wavelength, the energy emitted is small. Can you see? It's a kind of a bell curve. So for longer as well as for the shorter wavelength, the energy emitted is less. And there is a particular wavelength lambda m at which the energy emitted is maximum. So can you see they're talking about this particular peak, and this wavelength is lambda m. Right. So if the temperature is increased, then the peak shifts towards the shorter wavelength. So what do we mean by that? Suppose this is the graph, and this is the graph for, say, T1, and if we increase the temperature, the graph shifts in the left direction. The peak shifts in the left direction. So T2 is greater than T1. So Wien's displacement states that lambda m is inversely proportional to the temperature, and the constant of proportionality is known as Wien's constant, and it will be 2.82 into 10 raised per minus 3. Now let us see the question based on this concept. A solar radiation is found to have an intensity maximum near the wavelength range of 470 nanometer. Assuming the surface of the sun to be perfectly absorbing, calculate the temperature of the solar surface. So we know that intensity is maximum, so that will be lambda m, so 470 nanometer. And we know that lambda m times the temperature is constant, which is the Wien's constant, 2.82 into 10 raised per minus 3. Now from this we can find the temperature of the sun. So it will be 2.82 into 10 raised per minus 3 divided by lambda m, which is 470 into 10 raised per minus 9. So after simplifying this, we'll get the answer in Kelvin. So it will be 2.82 divided by 470. So it comes out to be 6 into 10 raised per minus 6 plus 9. So 6000 Kelvin. Now the next concept is Stephens-Boltzmann law. According to this law, if there is a body which is having a temperature T, and it is placed in a surrounding which is having a temperature T naught, then the rate of emission, let us say it is radiating energy, the rate at which it is radiating energy will be given as EA sigma T raised to power 4, and the rate at which it is absorbing energy, it will be EA sigma T naught raised to power 4, and the net rate of radiation will be U1 minus U2, which will be EA sigma T raised to power 4 minus T naught raised to power 4. Now let us see the question based on this concept. If the temperature of the body is increased by 50%, then the increase in the amount of radiation emitted by the body. So they are talking about the rate of radiation. So it will be U1, which is proportional to T raised to power 4. So if we increase the temperature by 50%, then we can say U1 prime upon U1 will be 1.5 T raised to power 4 upon T raised to power 4, which is 1.5 raised to power 4. And if you want to find the percentage increase in the radiation, it will be 1.5 raised to power 4 minus 1 divided by 1 times 10 raised to power 2. So that is the percentage increase in the radiation. So it comes out to be 1.5 raised to power 4, that will be minus 1, so it comes out to be 406.25%, right? So here I conclude this video. So I have covered all possible problem types that can be asked in JEE Mains 2025. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.